Chapter 12 is on radiation. Any material of temperature greater than 0 degrees Kelvin, whether it be a gas, a liquid, or a solid, on Earth or in space, emits and absorbs radiation. Radiation is the only form of heat transfer that does not depend on a medium to transfer through, meaning that radiation can travel through vacuum. Technically, there is radiation happening inside materials, but in this class we will consider radiation to be a surface phenomenon only. What I mean by this is that within the thickness of a wall, for example, each molecule is emitting and absorbing radiation, but we will completely disregard that in this class and only consider the radiation happening at the outer surface of the wall. The frequency of radiation, nu, is related to the wavelength, lambda, through the speed of light, which is denoted by c. The speed of light depends on the medium, but when light is traveling through vacuum, its speed is equal to 2.998 times 10 to the 8th meters per second. I will now go over some terminology. Emissive power, E, is the rate at which radiation is emitted from a surface per unit area. Its equation is E is equal to epsilon sigma times Ts to the fourth. Irradiation, G, is the rate at which radiation is incident on a surface per unit area, and it can be absorbed, reflected, or transmitted, and we will elaborate on that later. Radiosity, J, is the rate at which radiation leaves a surface per unit area, and for an opaque surface, the equation is J is equal to E plus rho G, where rho is reflectivity. So radiosity is equal to emissive power plus reflectivity times irradiation. Irradiation can be in the form of absorption, reflection, transmission, or any combination of the three. We define alpha to be the absorptivity, which means it is the fraction of irradiation that is absorbed. Similarly, rho is reflectivity, and it is the fraction of irradiation that is reflected, and tau is transmissivity, which is the fraction of irradiation that is transmitted. Since these are all fractions, then their sum must be equal to 1. Going back to radiosity, radiosity accounts for all the radiation that is leaving a surface, and that is why it is the sum of emission and irradiation. When radiation is leaving a surface, it scatters in all directions. So if we consider a small, flat area dA, the radiation it emits is along a hemisphere. Let's look at just a section of this hemisphere, such as this red arrow right here. Based on this drawing, we want to solve for d omega. D omega is called the differential solid angle, and it is defined as the following. The solid angle has units of steradians, which is the spherical equivalent of radians. And for a hemisphere, the integral of d omega is the following. The spectral intensity is the rate at which radiant energy is emitted at a given wavelength lambda in a given direction. This equation is per unit area of the emitting surface normal to the given direction, per unit solid angle about the given direction, and per unit wavelength. Similarly, the spectral emissive heat flux is the following equation. Note that the spectral emissive heat flux is based on the actual area, while the spectral intensity is based on the projected area. For all these terms with a subscript lambda, the subscript means that they are the derivative with respect to lambda. What I mean by this is that the integral of E sub lambda d lambda is equal to E. And this is what we now call the total emissive power. And the total emissive power is related to the total intensity through pi. Following the same trend as the spectral intensity and the spectral emissive heat flux equations, the spectral radiation is the following. The spectral radiosity represents the rate at which radiation of wavelength lambda leaves a unit area of the surface per unit wavelength. The subscripts of the spectral intensity are associated with emission and reflection. A black body absorbs all incident radiation. No surface can emit more energy than a black body. A black body is a diffuse emitter, meaning it emits in all directions. The equation for the black body spectral intensity is the following. And the black body emissive power is the following. C1 is equal to 3.742 times 10 to the 8th watts times micrometers to the 4th divided by meters squared. C2 is equal to 1.439 times 10 to the 4th micrometer Kelvin. This equation is known as Planck's law. As you can see from the figure on the screen, the spectral emissive power depends on wavelength and temperature, and the wavelength that results in the greatest spectral emissive power for a given temperature is based on Wien's law. Wien's law is lambda max times T is equal to 2898 micrometer Kelvin. The Stefan-Boltzmann law is EB is equal to sigma T to the 4th, where sigma is the Stefan-Boltzmann constant and it is equal to 5.67 times 10 to the negative 8 watts per meter squared Kelvin to the 4th. Moving away from black bodies and onto real surfaces, there are many equations which compare quantities such as emission, reflection, absorption, and transmission to their theoretical maximum values. For example, the total hemispherical emissivity is epsilon is equal to E divided by EB, and it is the ratio of total emissive power of a real surface to the total emissive power of a black body at the same temperature. Because spectral emission is related to spectral intensity, we can write the following. For absorptivity, we have similar equations. Notice that in this equation, the numerator is the irradiation absorbed and the denominator is the total irradiation that is incident on the surface. Similarly, for the top equation here, the numerator is the intensity absorbed and the denominator is the total intensity that is incident on the surface. Similarly, for reflectivity, we have the following equation. And for transmissivity, we have. I want to take a moment here to explain some subscript terminology from all of these terms that we've been talking about. You may have already caught on to this, but whenever we use the term spectral, the subscript for that term will always be lambda, and that means that you're basically taking the derivative of that term with respect to lambda. Similarly, the term directional has the subscript theta, and again, that is the derivative of the term with respect to theta. And so you could combine these. So if you have something like the emissivity here, where it is both spectral and directional, that means that it is the derivative with respect to both lambda and theta. Kirchhoff's law states that if there is one or more small surfaces within a large cavity of isothermal conditions, meaning that the cavity has a temperature of Ts, then the radiation from these small surfaces is negligible, and the cavity acts like a black body. Then, for these surfaces, the emissivity is equal to the absorptivity. Take a look at the following practice problem. We are looking for Q. The diagram probably reminds you of the solid angle diagrams I drew earlier, and you'd be correct in thinking that this problem uses solid angle equations. From the equation I presented earlier, we need to find I lambda e, but luckily we know that E lambda e is equal to pi I lambda e. The subscript E specifies that this is the intensity of the emitted radiation, and the subscript lambda makes these terms spectral, as they are the derivative with respect to wavelength. In this problem, we are given E1, which is equal to E sub E, and so we can rewrite the intensity equation as the following. Lastly, we use the solid angle equation d omega is equal to A2 cosine theta 1 over r squared, and plugging this all in, we can solve for Q. For part B, the total irradiation is the rate of incident radiation per unit area, and so we can write the following.